All right, let's do this. Welcome back to the channel, or welcome to the channel. I'm taping this. Today is a dark, kind of a gloomy day in Ireland with all this global warming thing. We're getting a bit warmer summers and wetter and duller winters. But look, you're here. I have something exciting today to go through. I'm excited. I mean, you're at the right place. You're doing the right thing watching this. So let's get going. What I'm going to talk about today is relays. Ooh, exciting, right? But we had kind of this true bypass is unspoken standard, I suppose, in DIY world, and we use these foot switches that have so many, contacts, and we use lots of wires, and I hate wires, right? And look at this. These are my tiny little relays that we can use to make our pedal be something a bit special. Everybody's like, it adds that high end when you can say, oh, my pedal uses a relay, whatever that means, Well, like, I'm not going to go in there, but like, you can see that this little relay can do lots of things. Now, I have to say before I do anything, careful what you're doing. Lots of coverages online of relays is talking about, how to use it with mains power. This is very dangerous if you don't know what you're doing. So I'm going to use signal relays. They're not rated for a huge current, but still, if you don't know what you're doing, stay away from mains. We're going to cover this, and this is more than anything else a reminder for myself not to do something silly. But here I have this 9 volt. Oops, sorry, what am I talking about? We are going to use 9 volt supply. We're going to use a battery, so we're pretty safe as long as we do just that. So what we have, when we talk about these pedal switches, they're big. When you click on it, it's mechanical. It latches in one position, latches in the other position. So it's pretty easy to incorporate this into your pedal. For using relays, we probably need to do something else. We need to use these momentary switches that can be a bit smaller than these. Something like this. You can use any of these. But the difference is that our relay, and you can see how small this is. I just want to kind of compare it to this TL072. They're tiny, compared to the switches. So we use mechanical action to switch this on and off, but the relay uses it's electrically operated switch. So if you go to Wikipedia, you can see here, a nice video look at that, how that works. And this is exactly what it has. Well, exactly. It has something similar to this inside, even though it's a smaller thing. There is a coil where we get some current through this coil. There is some what it does, it just drags these switches to one or the other position. For example, that is one of the ways to do it. There are other ways. It can this is, for example, this one in particular is monostable. So when there's no current, it sticks to one position. When you apply current, it goes to the other position of the switch. And this is, the simplest way to use it. So this tiny one here is monostable. Sorry, relay. It's this one. Yeah. It's, what is it? This is Axicom T connectivity. But for example, I've seen this one being used in what pedal do I have? I have Polytune 3, for example. Now, what's important to note here? This mine is 3 volts one, so it is very important to make sure that you have correct one. Their rating for your relay. As you can see, mine is IM01TS. IM01 is rated 3 volts, and it has this is the operate voltage. This is minimum voltage where it's going to be to activate the coil and change the switch position. This is the release voltage is 0.3 volts, and coil resistance 64 ohms. And these are important parameters because I want to make sure that I don't I couldn't find here maximum voltage for the coil, but normally you can go more than 150% or maybe 180% over before burning the coil. So we need to be careful about that. And this gives us an idea of current that this is using. So for example, 3 volts over 64 ohms, we are talking about something like over 30 milliamps, so this is important to know. So how do we use this? Let me bring up the schematic. I'm just wondering, meanwhile, did I cover everything I wanted to cover? Okay. Here I have the relay, right? So actually here I breadboarded all of this. Okay, so have the relay. I need to drive this current 33 or 30 something milliamps through the coil in order to make this work. So I'm going to use MOSFET. It's just easiest to drive this. And I'm not coming up with, if you want to have a look at how to drive any of these relays or anything as such, you can use, there's lots of useful information here where how to drive them, So for example, this is Panasonic's application note, applications of relays in electronic circuits. You can look it up, and it gives you a basic idea. I didn't come up with any of this, I was just reading documentation, and I'm not that clever to do this on my own, to be honest. And the smart thing is to read any application notes that you can, and that kind of gives you an idea of why some things are used, how to drive this. So I didn't choose transistor like this NPN because of the control circuit, which I will come back to. So MOSFET is just going to be easier to use for this. So you have things like, you have other things here, let me see if I can show this somewhere. Oh, jeez. Struggling today with the technology. So, you can go into general application guidelines, and it gives you, like what does all these parameters mean, you know, how do you choose which relay, there is some basic precautions and stuff like that. You should really read, and how do you, you know, organize if you use multiple relays, how they should be organized. And this is interesting because if you think about it, if you only want to turn on and off the circuit, you know, then we don't really need all this complexity, you know. So we go and we look at this, you know, we need to add some control circuit and we need to add some passive elements, etc., etc. But what is the benefit of using relays is that you can actually implement electronic control of this. So you could have something like MIDI device or something like that. For example, my Digitech Mummy pedal has MIDI input and it has relays, and then you can, you know, turn it on and off with a MIDI controller. On its own, that doesn't sound great, but if you think about it, you can organize them in several MIDI pedals that, you know, pedals that support MIDI, and then you can turn them on and off and change the arrangement, and you can do lots of different things. For this one, this is going to drive the relay. I picked up these kind of additional elements. So first of all, this one is just a indicator LED. So if you think about it, our switch has 3 switches essentially, but my relay has only 2. So I need something to indicate that it is on or off. And this is just for demo, you know, when the current is not flowing through the coil, it's not energized. This is the stable condition. This is why it's called monostable, because this is a stable condition. And then when you apply current, it goes to this second. It's really hard to talk about this position 1, position 2. But anyway, when it's on, yeah, my red LED is going to switch on, and my red LED here is going to be on, this indicator diode. And if when there's no current flowing here, this will be off, and the green LED is going to be lit up. So that's theory, of course. We're going to check that in practice. The other extra bits here is, for example, this is very important. My coil is rated 3. My relay is rated 3 volts. I should have used 9 volts. I didn't have them, so they didn't have them in stock or whatever when I was ordering. Doesn't really matter. We can still work away with this, you know. We can still add some kind of heating to the atmosphere through this, soaking it through this R3. Some of that voltage, we introduce voltage drop here, and thus we leave 3 volts on our relay. Not really. This is really important, but it's not really exciting. This is all this R3 does is make sure that we are within 3 volts. This flyback protection diode here is kind of important because when the power is cut here, what's going to happen is that electromagnetic field will start dissipating, or I don't know what the correct term is for this, but this will generate a spike of voltage inside the coil. And what's going to happen is that's going to add to the voltage there already, and it could be several times the of the supply voltage. So if it exceeds maximum value of our transistor, this is just going to destroy transistor. It probably won't first time around, but you know, we're going to use this coil several times, and then eventually it's going to break it. The thing is, I don't think that's going to happen here. This one is sturdy enough, and I don't know. But like, look, this is normally, this is I think reasonable precaution. So if we go back to that Wikipedia article, if we go to this page, we can see here there is how this flyback diode works, and you see the electromagnetic field, and it just flashes here really briefly and causes a spike in voltage. It's a bit not a great GIF, but this is how. Just try to see. You see it very briefly. It discharges anyway. This current that is generated inside the coil and prevents us from destroying the transistor. Okay, demonstration time. So I'm going to just wire this up. So I'm wiring this up here. So where's this? Okay. Oh no. I practice this, I promise. And still I fail. Okay, can you see that the green one is lit up? Yeah, it is lit up. So, and one of the interesting things that, this is very useful is that you can control the coil circuit that, I don't know how to say that, to control relay. You can use different power supply. So, and I'm going to do just that. Where do I need to plug this in? We just click this. We'll see in a second if I got it right. Yeah, I did. So I have my power supply and my battery, but you can see how you can use this with mains, for example. But just don't do it. All right? Not on my advice. Anyway, whatever I cover here, I'm not 100% sure that I even know what I'm talking about. So be careful. So how this works is because when the what you call this MOSFET is off, there's no current flowing through the coil. So I'm just going to go and apply. I'm just going to connect it to 9 volts here. If I'm just hey, and it worked. So as long as my MOSFET is on, I can just, this will be on, and I have both indicator and I have 2 switches. So that allows me to wire up pedal and have a proper true bypass. Yeah, it's off now. And it's a bit crappy, this green LED. It's not very visible, but you can see that it does that. And you can even possibly hear the sound of this coil performing, movement of that switching or whatever. Yeah. Okay, so that works fine, right? As I hoped it would. I just want to briefly go back to the diagram here. Just when there are certain things, you know, like, again, it's very hard to find information about, you know, using relays in a pedal. I mean, that's not really a common scenario, right? For general usage of MOSFETs and relays, you know. So I'd say what's the usage for that? Sometimes this does not work the way I expect it to work. So you see here, you know, you can feel pretty high, you know. We are using the things that are used within medical equipment and all this crazy stuff. Now, of course, we won't be. I'm not gonna even go near medical equipment design with my knowledge. But the thing is, it's not something that, you know, pedals are not something that's at forefront of you know, of using relays and MOSFETs. So lots of advice that you get is for various applications like controlling electrical motors or something like that, you know, like loads of different things. So and lots of times the challenge is in how quickly you can switch them on and off, you know, like we're talking about high switching frequency scenarios. So for example, this resistor here is normally used to prevent ringing of the control signal when it's, you know, fast switching. This here is preventing from parasitic capacitance inadvertently turning on the MOSFET. We spoke about flyback diodes. So these are kind of good things to design, to add to your design. I'm not 100% sure for pedal design what of this is critical or not, you know. So just kind of wanted to mention that briefly. One of the things that you can look up in these data sheets, for example, so look at this. We have this mechanical endurance is 10/8 operations. So we're talking about 100 million operations for mechanical endurance. What does that even mean? You know, just to give a context, this one has 10,000 mechanical operations. This one has 30,000, or, you know, this one can be 20. Depends on the manufacturer. Essentially, this is great if you have, for example, you can replace your just your pedal switch once you're, you know, if your switch goes bust, you can, you know, use that. So let me move on now to how do we control this? Okay, so obviously, if I had a switch and I wanted to use a switch, that would be great. You know, like, why would I even bother with this? But normally, when we see online these being used in situations where, you know, microcontroller is used, and you can use like something tiny, like 80 tiny, what is it, 13 has 8 pins, and, you know, it costs like a bag of crisps, you know, like it's super cheap, and it's great for this purpose, you know. But sometimes, you know, or you can use Arduino Nano or some other development board like Raspberry Pi or something like that. Those are really great things to try. But sometimes you want something simple, and in this case, you know, we might turn to Boss pedals, for example. Those guys figured it out, you know, like a long time ago. They have this, you know, their switches are not, their pedals are not true bypass. Lots of them. So we can, they use electrical circuit to control these, you know, they use JFETs for switches, blah blah. You can go and check, look it up online, Electrosmash and GeoFX websites. They have great write-up on these circuits. So have a look in description. I have a link to my web page that covers all of this. You can get all those links there. But this is an excerpt from Metal Zone MT2, just, you know, toggle switch operation. So I just ripped off that shamelessly. Here's my control circuit. Okay, so let me just show you this. Okay, it's visible, right? It's a bit of a jungle there. So I just use this really. So we have a switch. Doesn't really matter. We're going to use, for demo, we're going to use this one. This is momentary switch, only 2 wires. This circuit here is for the bouncing. So if you can imagine that switch, when it bounces these connectors here inside, there might be some kind of a instability in the signal. So this kind of smooths that bouncing and provides us with, you know, a better control signal here from the switch. This is just, you know, hardware way to do it. If you had a microcontroller, you wouldn't even need this. And now we have this toggle circuit, pretty much lifted from that pedal. Don't tell boss. But here, this is common. Like, this is not something that is not relatively well known as a circuit, and you can look it up online. On, I think there's on Wikipedia. There's also a simplified circuit of this. So, few things to note. I use different transistors. They have to be high gain transistors. I tried 2N3904. That did not work very well. It wasn't that stable, the operation. Everything else is pretty much the same. These are you probably need pretty close values here if you're using transistor like this. This affects biasing, but also affects the switching because of this combination. So how this works is, one of these transistors is always going to be on. So when, for example, this one is on, it drives collector close to the ground. But this collector is connected to base of this transistor. So if it is close to the ground, this one will always be off. Okay? If this one is off, this one is going to be high. This control voltage here. Likewise, if this one is on, this one is off, this is high. If it is on, this here is low. Make sense? But how does this work is that this quickly connects this signal to the ground. So there's it's high, this is pull-up resistor, this keeps it high, so our transistor is on. When we step on the switch, it creates a dip. And that pulse, negative pulse, no, zero pulse, doesn't really matter to the transistor that is off. But what it does is it turns off this transistor. For example, if this one was on, turns this one off because it quickly grounds this base, and this allows this transistor to be turned on. Something like that, if that makes sense. So that way, this maintains this toggle operation. You step on it once, this goes high. You step second time, this goes low. Step on it again, you get the drift. I changed this here because I needed a higher on voltage. or it's kind of a depends on how you really wire up your LED indicator, because you know circuit flips between on and off here, you know, high and low. That's a better way to put it. This one is just inverse of that. So it depends on how you wire up your relays. So if you know, like, and depends on what MOSFETs you use, you know, you just need to be careful how you wire it up, and in which case you need to lift up your LED indicator, you know, so you have it on at the right time. I don't know if that makes any sense. So let me get this connected. I have it here. I have it here connected. Let me plug in power. Okay. And let me just, I'm going to drive LED here just for this demo. This is my control wire. And hey, it's working. Yeah. So effectively, so now I'm going to connect this instead. So I'm just gonna wire it up real quick here. Go in. I need some juice here. If I can find, where's my, here. And okay, I wired it up. You can see this green LED is on, indicator is off. This, so, oh yeah, this is the indicator is off. I disconnected this. Well, no, that's embarrassing. All right, what did I do wrong? Actually, this is silly. I should have wired it up differently. So, this is my control circuit, and I wired up different circuit here. So this needs to go like this. And of course, we don't do this in pedals. You know, we're gonna use the same supply, so you know, it's all going to be fine. Let me see here. So, oh, I have it connected here. So all I need to do is wire this here. All right. I think I have it wired correctly. Yeah, hey. What do you know? I love it. Don't you love it? There's something calming about it. Okay. Ooh. So I would call this success. Yeah, we change this and replace it with this. I already feel this high end. I have this high end feel about all of this. Yeah. Now the thing is, we just I just said, you know, this pedal when engaged uses relatively high amount of current compared to the possibly pedal you're using. So for example, you use a booster, simple booster might be consuming like 1 milliamp, and you're using 33 or more milliamps for your relay. That sounds like a lot of emission and contribution to global warming. Of course, if you have higher voltage rated relay, it uses less current. So but in case you wanted to do something, to contribute to helping with global warming, you might, and you're conscious about your power consumption, there's actually a way to lower this this consumption. And this is really interesting because I have these two latching relays. They're bistable. Is that the word? Let me see if I can pull that up. So this is going to be, look at here. So this one is that I'm using. Again, it's 3 volts. I have a couple more, there are different voltages. And this is, again, the principle is the same. It's just you need to be careful when wiring it up. And a year ago when I got it, it was like half this price. So this is like, the prices have gone mad. And if you look at here, again, this is interesting because this is, look at that, has 100 million operations, and it can do 36,000 operations per hour. What's that? Is that every second or what? So there are a couple of important things here. There is, I'm using this one here, and you see rated current is 33.3 milliamps, and it drops as the number of as voltage goes up. But it's important to note that latching relays, they only need a short current impulse to turn it on. So here, it's somewhere here, I think. Minimum pulse width is 10 milliseconds, okay? So, you need that current only for 10 milliseconds. And why is that? Okay, so they work slightly differently. They're not, they usually have a magnet there that keeps these switches in correct position or desired position. Single winding model, it has a single winding of the coil, and in order to set the one value or to turn on one side of the switch, I'm struggling with terminology here or how to explain it, but like one position of the switch, you need to send a set pulse, and it is okay. You can see here that it's slightly different symbol. So when you send a positive pulse here, it goes to position 1. If you reset that, it goes to position 2, or other way around. So a reset signal is just positive on the other side, or it's a negative pulse, right? So this means that we have between 1 and 12, we need 3 volts to set one position, and we need -3 volts to reset the position, okay? And this is important for double wound coils. There's 2 extra pins that, so you activate one for one position, you send the positive pulse to the other one for the other position. But the important thing is that it doesn't, the current after that initial pulse, when the position is latched, it does not need any current, and thus you don't need you're good. You're not spending more current on it. Again, this one is here. It just happens to be the same resistance as the previous one, but because the current is lower, and I think resistance is higher here, but voltage is at this end is a bit lower. It just comes down to the same value. This is not a normal. That's not normally the case. Okay, so I have this. I have this here. Okay. So let me go through the circuit real quick. This is a clever circuit, right? It's quite clever. So this configuration here is red is on or in one position, green is the other position. There is a little element of how do you because this is a latching relay. If you leave it on, it may stay on. So it's a bit of a tricky bit to figure that out. Or what the recommendation is, you send a reset pulse and then you reset it and you know in which position it is. This is a bit tricky to do with our previous control circuit, but in this case it is fine. For this demo with controllers, it would have been just easy to do this with microcontroller. But let's go through this circuit real quick. So this is nothing special. We need P-type MOSFET because I just need I need to drive here with the 9 volts, so it is in it's slightly different configuration. We had N-type MOSFET connect to ground, and we had 9 volts here, and it when it was on, it would draw current. Here what we want actually when it's on to push current through this circuit that is energizing this coil. The thing is, again, the problem is this is using a lot of current briefly though, but it will our control circuit that we used previously cannot supply that current without jeopardizing operation of the toggle. So we need something like this to be able to push current through this. So how this works is when control signal is low, our MOSFET is on, so this charges this capacitor here through D1, C1, R4, coil, this diode, and R3. And that sudden rush of current sets the relay. When the control goes up, our transistor is off, and what happens is capacitor starts discharging through the transistor. So that way your inrush goes, your current goes through reset way, and resets the position. Now this is awfully clever. I had no idea you could do that. So what I did, this is what I got it from Omron's application notes. This is I'm just gonna go quickly. That's page 12. You don't really need to read all of that, I suppose. And can I zoom this? Yeah, this is useless. Yeah, so essentially what I said there, it's exactly that. All I needed to do was size the components correctly. I think I got that. We'll see that in a moment. All right. So, but I have, again, how to find this. It says safety precautions for all relays, but this is not just that. There's very good information on circuit as well here within this document. So I have it wired up here. Okay, I need power, right? So here's my battery. It's here. Where is this? Yeah, so I think I got this here. Okay, so you can see here, red is on. Let me get this here. So positive is here, negative is here. Just need to rewire. Okay, so how I have this set up is my control circuit here is wired up with the power supply. My battery is wired up here. What I'm going to do is I'm going to get my. So let me see how I'm going to do this. Now this one is high. All right. So when I did my control circuit high, it just switched. I disconnected, connected, disconnected, connected. So I was playing with this before, so I don't need this. So is the current flowing through this? You know, you would wonder, you know. So you can just unplug it, okay? So because, as I said, you know, there is current inrush, and it's a sensitive kind of a device. So let's see if I can check this. If I can show anything. So I'm just gonna see what is this is our 150 ohm resistor, I think. Yeah, it is. So this is a measuring resistance. That's not what I want to show. See, there's no voltage drop on this. There's so that means there's no current. You see, I just removed it, and then it just fluctuates here. So there's no current flowing. So I'm just gonna switch this, and let's measure it again. There's no current going, right? So just tells you that there's no current. Obviously, the circuit is still on here. The capacitor keeps charge, and there will be some trickle current that keeps the capacitor charged. But the thing is, it's going to be minuscule compared to, we're talking about microamps, as opposed to tens of milliamps. So let's demo this. I think I can just disconnect this. I don't need this. Okay, so let me. Oh, I actually need this. All right, let's. This is positive end. I need it. Oh yeah. I should be really using red one for this, huh? It's the black one is longer. So look, we'll do with this. I connected this. Yeah. I hope it shows. I have the switch. Does nothing because I haven't connected here. Oh! It's working. And it still doesn't draw any current. And I think this is great, right? So I think we covered everything I wanted to cover here. It took us a while because I can't do it quickly, as you may know. So where do we go from here? Just make sure that you look at my website, get the links. I cover which relays I used, how everything is there. What I'm going to do is, probably in some other video, I'm going to incorporate this into a pedal. But until then, you know, I hope this was exciting, you know. I think it was quite interesting. Again, if I can offer an advice, use this bypass switch unless you really want to use a relay for something that is more advanced. Next time I'll probably go and do something with microcontroller, because that, I suppose that makes sense. I can use this circuit. It's very useful. We learned a bit about it. I don't know if I would go with this latching relay unless I was using controller. You know what? If you want to save the earth, you know, walk more, eat less red meat, I suppose. I don't know. Some options, and, you know, use whichever relay is easier to use if you want to use that, you know. That's it for me. Until next time.